Now we'll talk about mass percentages and how you can use mass percentages to determine the empirical formula of a compound. For this problem, we're going to consider the molecule methane, or CH4, and we're asked to find the mass percentage of hydrogen in this compound. So how do we approach this problem? How do we go about solving it? Before we think about finding a mass percentage, let's think about how we would calculate percentages in everyday life. So remove ourselves from a chemistry example for a second. And let's say that I wanted to know maybe what percentage of the students in this class wear glasses. The way that I would calculate that would be, I would take the number of students who are wearing glasses, divide it by the total number of students in the class, and then multiply by 100 to make it a percentage. The same sort of idea applies here, right? We're going to take the part that we're interested in and divide by the total, multiply by 100 to make it a percent. So to find the mass percentage of hydrogen, what I can do is take the mass of hydrogen, right, because that's the part that I'm interested in, and then divide it by the total mass of CH4. That gets multiplied by 100%, and that gives us a percentage. All right, now the problem is this question doesn't give us a mass of anything. So let's think about where you can find information about masses. Periodic table is a great place to look for that. So we can go to the periodic table and use molar masses in this equation. All right, so for our mass percentage of hydrogen, the mass of hydrogen in CH4, we recognize that there are 4 hydrogen atoms. So you're going to have to multiply 4 times the molar mass of hydrogen atoms. So that's 4 times 1 gram per mole. Divided by the total mass of CH4, carbon is worth 12, and then 4 hydrogens, so that's plus 4 more, gets you to 16 grams per mole times 100%. The grams per mole cancel out, and all I'm left with is a percentage value, and that number is 25%. So 25% of the mass in CH4 is hydrogen. What's the rest? Carbon, right? So carbon, it must be the remaining 75%. Now let's introduce the concept of empirical formulas. Empirical formulas are formulas for compounds that are obtained experimentally. That's what the word empirical means, that it comes from experiment. And an empirical formula tells you the simplest whole number ratio of atoms or moles that you have in a molecule. Generally speaking, you can find empirical formulas starting with mass percentages, and that's what we're going to do in this example. There are other ways you can find empirical formulas, and you'll see that in a later video. But in this video, we're going to talk about how you can use mass percentage data to find an empirical formula. In this problem, you're told that a compound contains only phosphorus and oxygen. You're told that it's 43.7% phosphorus by mass. And you have to find the empirical formula for the compound. How are we going to go about solving this? I think it's really helpful to begin problems with the goal in mind. Think about what the answer looks like and what type of information you need to solve this problem. In an empirical formula problem, we're going to need to know mole ratios, because I'll remind you again that an empirical formula tells you the simplest whole number mole ratio in the compound. So we must find mole ratios. You can find either the ratio moles of phosphorus over moles of oxygen, or you can find the ratio of moles of oxygen over moles of phosphorus. But that's what we're looking for, is a mole ratio here. In order to do that, we're going to have to find moles of phosphorus and oxygen, right? So what I'm doing here is I'm taking the goal of the problem and I'm using it to kind of think backwards through what are all the steps that I need to do in order to solve this problem. This will allow me to devise a strategy for solving even the toughest of problems, even a problem that you've never seen before, like this. All right, so we need to find the moles of phosphorus and oxygen. Now, the problem is this question doesn't give me a number of moles. What we're given is a mass percentage. So that's going to be a little tricky to see how we get moles out of that. But we can get through this, because let's think about what the mass percentage can tell me. A mass percentage can give me a mass of phosphorus and a mass of oxygen. And then, from the mass, we can get to moles by using the molar mass. Once we have moles of phosphorus and oxygen, then we can make mole ratios and solve the problem. Problem here is, we're just told the percentage of phosphorus by mass. We're not actually given a mass of phosphorus. And so what we can do is, when the problem doesn't specify a mass, we can assume a sample size. And let's think about what would be a good amount to assume. You could pick any number you want, but I think the number that's the easiest to deal with is 100 grams, because when you deal with percentages, 100 is a nice number to work with. All right, so we're going to assume a 100 gram sample. And if we have a 100 gram sample, then that means that we have 43.7 grams of phosphorus, and the rest has to be oxygen. So 100 minus 43.7 comes out to 56.3 grams of oxygen. Now we know masses of phosphorus and oxygen. We can convert the masses into moles, and then use the moles to get the mole ratio and solve the problem. All right, I just moved everything up to give a little bit more space. So now we're going to convert mass to moles. For the phosphorus, we have 43.7 grams of that. And from the periodic table, the molar mass of phosphorus is 31 grams per mole. Put the 31 grams on the bottom so that the units cancel out. This sample has 1.410 moles of phosphorus. For the oxygen, we have 56.3 grams of that. Periodic table tells us that 1 mole of oxygen weighs 16 grams. And when you calculate that out, you find that you have 3.520 moles of oxygen. Now we've found the moles. The next thing to do is to find mole ratio. The guiding principle here when making the mole ratio is that it's helpful to divide big numbers by small numbers, because that will make it a little bit more straightforward to see what the formula should be and what the correct ratio should be. So divide big number by the smallest number. All right, in that case, that means we're going to be doing moles of O over moles of P. All right, so for our ratio, moles of O over moles of P, we have 3.520 moles of O divided by 1.410 moles of P. You could plug this into your calculator and you'll get 2.5. Now, it's nice to have that number written out, but it's good to give it physical meaning. And the units give things meaning. And the units are moles of oxygen per mole of phosphorus. All right? So this is not just some random 2.5 number. This number does have meaning, and writing the units helps you to see that. For every 2.5 moles of oxygen, you have 1 mole of phosphorus, right? Because there's like a 1 that's implied here in the denominator. Or you could also say for every 1 mole of phosphorus, you have 2.5 moles of oxygen. With that being said, we can now write out that this compound contains phosphorus and oxygen, right? And the mole ratio tells you that for every 1 mole of P, you have 2.5 moles of O. Now, this is not the simplest whole number ratio, because we recognize that 2.5 is not a whole number. So how do we turn this into a whole number? Well, you can multiply everything through by 2, right? That would convert 2.5 into a whole number. So now we convert to whole numbers. Multiply everything through by 2. So that's going to be P2O. 2.5 times 2 is 5. P2O5 is the empirical formula. That's the simplest whole number ratio of moles that you have in this compound. And there we have it. All right. Next, we'll talk about the connection between empirical formulas and molecular formulas.